morning. Good morning, everybody. My name is Sonja Reinhardt, and I'm the Science Center Coordinator here at the University of KwaZulu-Natal Science and Technology Education Center. And I would like to welcome you to this very exciting place, and I hope that you're going to see lots of interesting things. We're going to go through the Geology Museum and through the Science Center later on. But before we're going to do this, let's start here. So what this one basically simulates is a tsunami. Okay, does anybody know what a tsunami is and how it forms?
When the tectonic plates in the sea overlap each other and then it pushes the water from the sea to come onto the land.
So what you have to imagine is that you need a large displacement of water. Through earthquakes, you can get this when you have tectonic plates, and they move towards each other and one dives underneath one plate. So what basically happens is that the plate dives underneath and, you know, it's getting a little bit stuck. Okay, so and suddenly it releases the other plate and the plate bounces up and therefore displaces lots of water. Okay, so did you notice something while I was talking? What happened with the water?
It's gone back.
So the water, yeah, you're right. The water kind of pulled back. And not like your normal tide, you know, you go to the beach and then the water goes out for 6 hours and then comes back and so on. It's different. So here the water pulls back within minutes. So what are you going to do if you see water pulling back?
Run.
Yeah, run. But the question is, where are you going to run to? In which directions are you going to run? To the mountains. Okay, so we have two animals here. So if you want to place them, one maybe where you think it's not safe and one where you think it's very safe on the model. And we'll see if they're going to survive or not. Tsunami, did you survive? So who survived? The horse on top. Okay. Where was the safe place? High up. Okay. So also what you might have noticed is that the water is not coming as a single wave, but more like a couple of waves. I don't know if you noticed that in the model. So what you basically have to do is you move to higher ground if you see the water pulling back very far out, and you have to wait, because often, you know, the arrival time of the first wave and the arrival time of the second wave, it can take up minutes. I'm pretty sure, yeah. So I'm pretty sure you've learned, you know, about periodic tables, about the elements in school. But have you ever seen the real elements behind it? Okay. Oh God, yeah. Everybody wants to see gold. Yeah. Gold is boring. Okay. Anyway, so here's your gold.
Wow.
Okay. So and this is actually how you find gold in nature. So it's in a rock, or you can find it as a nugget. But you know, everybody thinks, you know, gold is so super duper expensive and so on. So the one that is right next to it, the platinum, is way more expensive.
Copper, isn't copper quite valuable as well?
Yeah.
Especially because of the cables.
Yeah, the cables, but still because you have so many. So rhodium is not very common. Copper is way more common.
Right.
So of course, the more you have, the lower your prices are. Okay, so and you can see the various varieties. So what we try to do here is basically we show the real mineral or element, and copper comes as a native element. Okay, so as a native element, and then the applications. So you have your copper wire. So here you've got your money.
Yeah. This means it's toxic.
No, this is in fact a symbol that says that it's radioactive. Okay, so all these ones with a triangle in it, those ones are radioactive.
And those are the people that discovered it.
No. but it was close. No. Okay. So it is quite interesting. So a lot of these ones are actually formed in the HEI, so heavy iron. So they're man-made. Okay, and there are various centers around the world. So there's one in the US, which is in California, in Berkeley. And this is why you have minerals, elements named after like berkelium, californium, and things like this. They are basically named by the institution after the, or americium, after the country and the province and the place. Here, this is a plasma ball. So what you have inside here is an electrically charged gas. And you see what you see here, these stars are discharges. Okay, who wants to touch it?
I think he should touch it.
I don't want to get shortcut. It's like the current is coming straight to my finger.
Exactly. Yeah. So it's concentrating. So because you are basically the lowest resistance, it's concentrating now all the charges in one point. You can see that this charge is getting less and less. Okay, can you see that? So,
Well, you can play with this folder.
yes, I know, but this is even cooler here. You know what this is?
It's the light bulb.
It's a light bulb. How do you light a light bulb? What do you need?
You need
Electricity, yes. So, well, I can hold a light bulb in my hand and lighting it up.
Oh wow, that's interesting. So how does the electricity get passed to the bulb?
So inside here, you also have an electrically charged gas. Okay, so when you apply an electric current, it basically that's what lights up. So just like here. So remember, we're looking for the least resistance. So now the electric charges are now going to be passed over to the light bulb. You want to try it out, okay? And what I want you to do is I want you to move. Take this hand and move the hand up.
So it's getting limited by the hand.
Yeah, it is
It's because
limited.
we're conductors.
Yeah,
So it's using us just to
yeah.
go it up.
Yeah.
Wow.
Look there. Look there. Look at you controlling the light.
You can just light up the whole house.
Okay, this is
Put 10
interesting.
lighters
You must
around.
put this on your Insta stories.
Yeah.
So what we've got here, this is what looks like an ordinary disc. This is in fact a hovercraft. When I put this one onto the floor, it wouldn't kind of move very far. And we can try this out. Okay, so if I'm going to put it down like this, and you try to push it, try it out. It's very difficult actually to push. Huh? It is, eh? It's not really, and especially now if somebody's going to sit on it, who's going to sit on it?
Okay, I'm gonna.
Yeah, I was going to say, not this. You're welcome. It's your time.
Okay, you have to sit, and you have to sit in the middle. You have to sit in the middle. Okay, and now I come with a little bit of air. Okay. Right. All right, are you ready? You can push it back, push it back. So do you see the difference?
Yeah.
So now you're hardly able to
And
push.
because you're lifting him.
So when you look at it, you see these holes here, and this is basically where the air pushes through, okay, from the leaf blower, okay, and then it forms a very thin kind of pocket of layer of air. So and it reduces the friction on the floor. So friction is basically the resistance on the floor. So when you move your hands over something rough, you have more friction as if you move your hands over something very smooth. Have you ever looked at sand through the microscope? Okay, so I'm gonna show you some really cool sand. Okay, so basically what a microscope does, it makes small things look bigger. Exactly. So, and what I've got here is something that you might not have ever thought of looking at through the microscope, and this is sand. And I've got some very special sand here, and this is Durban beach sand. Okay, so, and you might think, oh no, Durban beach sand is not really special. So I don't know if you've ever been to the Durban beach?
Yes.
Yes. Okay, so have you ever noticed these black strips alongside the beach? The black spots? So what do you think what they are? Okay, so people often think it's oil, and you know, the sand looks really dirty, it's oil or some other dirt. And now the microscope is going to reveal what it actually is. What you will notice is the sand, but also you see black grains. Do you see them?
Yeah.
What I've got here, this is the heavy mineral sand, this is just ordinary sand, and I just want to feel you. Do you notice a difference?
Yeah, this is heavier.
This is heavier than this one here. Does everybody know what this is?
Magnet.
It's a magnet. Okay, so, and now what I'm going to do is, I can actually extract some magnetic minerals out of the Durban beach sand. You want to try it out? So what is special about this sand is that it's mined up in Richards Bay. So the magnetic mineral contains iron, but there's also minerals that contain, for example, titanium in it. So your ilmenite, and here we have some rutile with some garnet in here. So they contain titanium, and this is what they're mining up for in Richards Bay, for its titanium, so that you can convert into titanium dioxide that makes your paint white, your paper white, and so on. And also we have zircon, and this is a special material, for example, for your screen. Some people use it to make very scratch-resistant screens. Okay, so if you want to follow me to have a look at some cool rocks. So remember you have your three main rock types. You have your sedimentary rocks, they are over there. We have our igneous rocks. So these ones are basically rocks that come from, volcanoes. So you have your extrusive rocks. And then we have our metamorphic rocks, which are basically reworked, either metamorphic rocks or reworked sedimentary rocks or reworked igneous rocks. Okay, so I've got some very special rocks here, and this is for really, this is for really strong men and women. Okay, so you need both hands, and it's super duper.
Looks so small, but it's heavy.
It is heavy. You just want to pass it around?
But it's a pretty rock.
It's very pretty. It's like the lights.
Okay, and what is special about this rock? Yeah, this is especially bad when you have a compass and then you try to take the reading, because your compass goes all over the place. Okay, so that is a banded iron formation or banded ironstone, where you have layers of metal in between that are basically magnetic. And then this is actually from close by here in KwaZulu-Natal, from the White Mfolozi River. So where you find lots and lots of interesting, or lots and lots of these banded ironstone. And banded ironstone is also very important because they are the first indicator of oxygen in the atmosphere. And these rocks often date back, I think, I'm not too sure I think they're around 2,800, 3,000 million years old, these rocks. So very old. Okay, so, and now, this is seriously for the strong man.
It's light.
Are you sure?
Yeah, it is.
Just pass it on.
Oh, yeah, very light.
Like a sponge.
Yeah.
Is it found at the sea?
No, this is in fact a volcanic rock. This is a froth version of this rock here. So this is an obsidian. So that's volcanic glass. Okay. So you can see it's quite shiny and just like glass, you can use it actually as a cutting tool. So imagine a Coke bottle. You have some liquid in it, okay? Or some Coke or whatever. So just imagine that this is your magma. So now when you start shaking it up and you open it, what do you see?
It fizzes out.
It fizzes out, so foam is coming out. So this is actually exactly what this is. It's foam. It's foamed obsidian or foamed glass. And also, ladies, what you might notice is you can use it to scrub your heels, because this is pumice. This rock here, okay? So this rock here, and it looks ugly, hey? Let's put it like this. But it is actually a quite interesting rock. Can you see these lines here? Yeah. So what you're basically looking at are mud cracks. Do you know what mud cracks are? So when you have very very fine-grained sand and you have water coming in and it dries up, then you see your patches crack up. So that's what they call mud cracks. And so what is quite interesting is, what do you think how old this rock is? I know this is a stupid question, but because you probably won't know. But I love people to guess, you know. So I can prompt myself to be very clever because I know the age.
Age of the dinosaurs.
Okay, so age of the dinosaurs. So that's round about, you know, depending on what kind of dinosaurs we're looking at, up to 250 million years. Okay.
I think quite recently, maybe 10 years.
10 years. Okay.
Stone Ages, I don't know.
Stone Ages. So that's like, oh God, now I have to go back like 10,000 of years. Okay. All right. If I'm going to tell you that this particular rock is about 2,700 million years old, so 2.7 billion years old.
Older than dinosaurs.
Older than dinosaurs. So they've already seen it. They've seen everything. Dinosaurs, humans. And what is quite interesting is that geologists also use rocks to learn something more about it. So what we know is, we know now what kind of condition this rock was formed 2,700 million years ago. It must have been had some form of water. Okay, so here we go. Even though we weren't there, we can look at rocks and then figure out what basically happened. This is a typical kimberlite. And kimberlites come in all sorts of different weird forms, looks, and so on. And this is how you would find diamonds. And these ones are basically rocks from a diamond mine high up in Lesotho called the Letseng Diamond Mine. And they produce very, very large and nice diamonds. So I was very lucky at one point to hold a diamond about that size in my hand, a raw diamond. I mean, this is like seriously nice. It was seriously nice. Seriously nice. Okay, but you know, these kinds of rocks are also interesting for other things. Not only bring they up diamonds, but they also bring up rocks from very, very deep down. We know now how mantle rocks look like because things like kimberlites bring them up from deep down. So this is a very typical rock. So this is a granite, okay? And you can see this, some of these shiny black things here. This is in fact mica. This is a volcanic rock. This is a basalt. And this is also a volcanic rock. This is a rhyolite. And can you guess where they're from? They are in fact, and you might have seen them actually. They're actually here from South Africa, from KwaZulu-Natal. So this one here you find on the top of the Drakensberg mountain. And this one here you find when you go up to Jezini, Lebombo Mountains. And coming to our metamorphic rocks. And sorry to say I'm biased because I love metamorphic rocks because they are so pretty. This is the non-scientific name that some of our former students said. How it's called glitterite because it's a glittery.